All right, this is our section on 7.3, sampling distributions for sample means. Here's what we're going to learn in this section. Starting with the sampling distribution of X bar. When we record quantitative variables, we are interested in other statistics like mean or median, standard deviation. Those are the most common that we're going to use. If we look at the mean household earnings for sample sizes of 100, if we look at the population distribution on the left and then a sampling distribution on the right, what's the difference between the shape, center, and spread? So sampling distribution, instead of just being a sample of a bunch of households, this one is a whole bunch of sample sizes of 100 of households. So what happens when we take means instead of just straight data is looking at the population distribution of the samples, everything is a lot more condensed. So the mean, let's see if I can right here. The mean of the distribution becomes more centered. And the distribution itself, looking at spread, is less variable. The larger your sample size is. Oops, sample size. Okay, so that's the difference, is that we can see the mean is more in the center of the tallest area instead of skewed over towards the right, and then it's a lot more condensed. Okay, when we choose many simple random samples from a population, the sampling distribution of the sample mean is centered about the population mean. That's where the tallest area is, and it's a lot less spread out than the population distribution. So the mean of the sampling distribution for mu of X bar is just mu of the population distribution. The standard deviation of the sampling distribution of X bar, sigma of X bar, we take the sigma, which is the standard deviation for the population distribution, and divide it by the square root of our sample size. In order for us to do this, we have to have the 10% condition. Okay, so now we can apply this to an example. The height of young women follows a normal distribution where the mean is 64.5 inches and the standard deviation is 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches, showing your work. So this is not the new information. This is not the sampling distribution of X bar. This is just finding the z-score for this specific young woman who is 66.5 inches tall. So what we have to do is take the statement they're asking us, find the probability that someone is taller than 66.5 inches, and convert that to a z-score. So to change the x to a z, we take x minus mu over sigma. And that information was given to us. Okay, we calculate that. The z-score we get for that is 0.8. And then since this is a greater than probability, we have to find the number on the table and subtract it from 1. So the number on the table that I find is 0.7881. I subtract it from 1 and get 0.2119. So that is just reviewing stuff we've done before with z-scores. Now if I'm trying to find the difference here is that I'm trying to find the mean height of a simple random sample of 10 young women exceeding 66.5. So notice on letter A, it's just looking at one randomly selected young woman versus looking at a mean height and 10 young women. So this is actually asking for X bar being greater than 66.5 inches. And the difference, the only thing that is a difference in this calculation is that the sigma on the bottom now needs to be divided by the square root of the sample size. So I can still convert it to a z, 66.5 minus 64.5. Oops. But this time we are dividing by 10. We're dividing by, oops, 2.5 over the square root of 10 because we have a sample size of size 10. Okay, so mostly looks the same except for the square root of 10 on the bottom. So this time our z that calculates into is 2.53, which is a lot different. And again, since it's greater than, we take what we find on the table and subtract it from 1. And get 0.0057. So why do we think that's such a smaller number? On just looking at one woman, we have 0.2119, and for a sample size of 10, we have 0.0057. If I even just look back at the picture that we had over here, look how much more spread out the population distribution is versus the sampling distribution. Way more spread out. So it makes sense to me that if I am looking at a value greater than, on this case, in this picture, 100, there's a lot more than there is on this one, greater than 100. So the reason for that with our calculation is that we're dividing by a smaller number. So here we're dividing by 2.5, where here we're dividing by 2.5 over the square root of 10. So that's actually quite a bit smaller of a number, which means our probability is going to be a lot smaller. Okay. So the relationship, if the population distribution is normal, then the sampling distribution is also normal. And that doesn't matter what the sample size is. So as soon as the question states, okay, the population distribution for this is normal, then we can go ahead and do normal calculations with the sampling distribution. Okay, yeah, so that's what that says. We have a population distribution that's normally distributed, so then we can calculate the sampling distribution of X bar as long as the 10% condition is met. So here's another example of taking a population distribution and turning it into a sampling distribution. The length of human pregnancies from conception to birth varies according to a distribution that is normally approximately normal. The mean is 266 and standard deviation is 16. Find the probability that a randomly selected woman has a pregnancy that lasts for more than 270 days. So this is the basic Z calculation where we're just looking at one woman. So we have here the probability that X is greater than 270. And then we can turn that into a Z score. X minus the mu, which they gave us, is 266, over the sigma they gave us is 16, which turns into a Z score of 0.25. And we get the probability after subtracting from 1, since this is greater than, we get a probability of 0.4013. Now we're looking at the same kind of information about the pregnant women and the length of their pregnancy, but we're looking at 6 pregnant women all at once. So this is a sampling distribution. What is the mean of the sampling distribution? It's going to be the mean that they gave us for the normal distribution. It's going to be 266. Compute the standard deviation of the sampling distribution. So that's going to be the standard deviation that we had of above of 16, but this time we're dividing by the square root of the sample size, which is 6. I'm going to leave it like that because it's going to be more accurate that way. The 10% condition is that our sample is less than a tenth of the population, which it certainly is, because if we only have 6 women, there are definitely more than 60 pregnant women in the world. So we have the 10% condition met. Find the probability that a mean pregnancy length for the women in the sample exceeds 270. So our calculations will look pretty similar, only our sigma on the bottom is going to be 16 over the square root of 6. So the z-score, after we divide by our new standard deviation, 16 over the square root of 6, our z-score is 0.61. And the probability after subtracting it from 1, since it's greater than, is 0.2701. I'm again noticing that because this is a sampling distribution calculation as opposed to the one woman up above on number 1, my probability is decreased. And again, that's because my standard deviation is smaller when the sampling distribution has more condensed data. Okay, so before we mentioned that if we have a normal population distribution, then we have a normal sampling distribution. But most of them are not going to be normal, like not very many in the real world are normal distributions. So what happens if we start with a population distribution that's not normal? What's really interesting is that as we get bigger sample sizes and then we look at the sampling distribution, it's going to look more and more like a normal distribution. So the central limit theorem says when we get a larger size n of our samples, then the sampling distribution for x bar is approximately normal. So even if we know that the population distribution is skewed, as long as we start with a large enough sample, then the sampling distribution is going to be normal, and we can use normal calculations on it. Okay, so here we're looking at a population distribution. That's the top one, the one in the gray from Rice University. And then as we go down, this is the population again, and then now we're taking distribution of means of different sizes. So we're starting with a sample size of 2. It still looks very irregular. Going down to 5, it's starting to look more bell curved, but has some high bars in weird places. And then as it gets bigger, 10 looks very normal, and then 25 it looks even more normal and further condensed. So what would we say? As n increases, we notice that the larger the sample size, the more normal the sampling distribution is. Despite the irregularities in the population distribution. Okay, so to re-emphasize the importance of the central limit theorem, this is a really big deal. Even when we start with a population distribution that is not normal, it could be really off like the last one was, the sampling distribution of the sample looks pretty normal as we get to about 25. I've mentioned before we have kind of a magic number for looking at normality, and that magic number for the sampling distribution is 30. So even if we start with something that's not normal at all, the sampling distribution of X bar is, as long as we have a large enough sample size. We can't just say, okay, well, it's not normal, but I have a sampling distribution, so it's got to be normal. We have to make sure that we have a large enough sample size first before we can state that. Okay, so we can use the normal calculations with z-scores in our z-table to answer questions about sample means, even if they come from a population distribution that's not normal, as long as our sample size is big enough. So let's do one question about that. Your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on service records from the past year, the time that a technician requires to complete the work follows a strongly right-skewed distribution, where the mean is 1 hour and the standard deviation is an hour as well. In the coming week, your company will service a simple random sample of 70 air conditioning units in the city. You plan to budget for an average of 1.1 hours per unit. So that's the average, that's the important information. Will it be enough? So we also need to know the population mean and population standard deviation for this calculation. Since it's asking about an average, our probability statement involves X bar. And we want to know if that's enough time. What's the probability it'll take longer than that? So now I can convert this to a z-score knowing the mean and standard deviation of the population distribution and the sample size of 70. So 1.1 minus 1 over our new standard deviation of 1 over the square root of 70. That z is 0.83. Since it's a greater than probability, I have to subtract it from 1. On the table, I get 0.7967, so my probability is about 20%. So about 20% of the time, I'm going to go over 1.1 hours. So to summarize this question, I'd say about 20% of the time, the technician will go over. Which is not ideal. Okay, and then we have one more picture to kind of summarize this section of the population distribution, or the sampling distribution rather, where X bar is in the middle, the mean of X bar is in the middle, and then the standard deviation is sigma over the square root of n. Okay, and our homework is listed on the bottom. We talked about what we learned how to do in this section.